Hi, in this video, we are going to continue our course on polynomials, and I'm going to look at certain applications of trigonometry in polynomial problems. So let's begin by looking at this particular question. This is question 1. Find the least positive integer n such that the polynomial p of z is equal to root 3 z power n plus 1 minus z power n minus 1 has a root on the unit circle. This question is from the Moldovan National Maths Olympiad in 2008. Olympiad 2008. Now, let's think about how we would approach this particular problem. We have to find the least positive integer such that this polynomial has a root on the unit circle. The root on the unit circle means the modulus of the root. For example, if there is a root z, therefore p of z must be 0, and since the root z lies on the unit circle, mod z is equal to 1. Because it lies on the unit circle, the radius is 1, so mod z must be 1. So therefore what we can say, rewriting this equation, root 3 z power n plus 1 minus z power n is equal to 1. When we say pz is equal to 0, this is how we rewrite it. What we can do is take z power n common and we get root 3 z minus 1 is equal to 1. Now what we can do is take modulus on both sides. So modulus of z power n root 3 z minus 1 is equal to 1, which means that mod z power n and mod of root 3 z minus 1 is 1. And because we know that mod z is 1, this part will become 1, mod of z power n. So we get from this that root 3 z minus 1 modulo is 1, right? Now, this is where we have to use our trigonometry knowledge. We have to find the z such that, find the condition on z such that this is true, right? So what we will do is we'll write z as cos theta plus I sin theta. Because it's a point on the unit circle, you can write it like this. This is 1 ei theta, right? So we have root 3 z minus 1 is 1, and putting z as cos theta plus I sin theta, we will get root 3 cos theta minus 1 plus I root 3 sin theta. Modulus is equal to 1. This is the equation we get. And taking the modulus square for this complex number, we will be able to write it like this. Root 3 cos theta minus 1 whole square plus 3 sin square theta is equal to 1. This is the condition that we get. If you simplify it a little bit, take 3 cos square theta and combine it with 3 sin square theta, what you will end up getting after a little bit of simplification, you will get 4 minus 2 root 3 cos theta is equal to 1. And from there we get cos theta is equal to root 3 by 2. So basically theta is coming out to be plus minus pi by 6 or 30 degrees. Theta comes out to be plus minus pi by 6. And now we can put this theta in the original equation. So what was our original equation? It was root 3 z power n plus 1 minus z power n minus 1 is equal to 0. And now if I put theta is plus minus pi by 6 and z is cos theta plus I sin theta, if I put it in the original equation, I get root 3 cos of plus minus pi by 6 plus I sin of plus minus pi by 6 to the power n plus 1 minus cos of plus minus pi by 6 plus I sine of plus minus pi by 6 power n minus 1 is 0. Simplifying this by using De Moivre's rule, we get root 3 cos of plus minus n plus 1 pi by 6 plus I sine n plus 1, this is also plus minus, n plus 1 pi by 6 minus cos of plus minus n pi by 6 minus I sine of plus minus n pi by 6 minus 1 is equal to 0. I have just used De Moivre's theorem here, which says that if you have cos theta plus I sine theta and you raise it to the power n, that becomes equal to cos of n theta plus I sine n theta, right? So that is what we have used and simplified it like this. Now this equation is basically having a real term here, a real term here, and two imaginary terms. So it's like a complex number being equal to 0. So you can equate both the real and the imaginary parts to be equal to 0. So what we get is first this equation, root 3 cos of plus minus n plus 1 pi by 6 minus cos of plus minus n pi by 6 minus 1 is equal to 0. This is the real part of the complex number. And secondly, we get root 3 sine of plus minus n plus 1 pi by 6 minus sine of plus minus n pi by 6 is equal to 0. These are the real and the imaginary parts. Now, how do I simplify this? I will take the one on the other side. I will work with the first equation first. So I will do it here. This is, take the one on the other side. 1 is equal to root 3 cos plus minus n plus 1 pi by 6 minus cos plus minus n pi by 6. This is the equation. So what we can do here is basically write this as expanding this expression. We can write it as root 3. This is n pi by 6 plus pi by 6, right? So we will get cos of, basically it is cos of plus minus n pi by 6 plus minus pi by 6, right? So expanding it, you get cos of plus minus n pi by 6, cos of pi plus minus pi by 6, and minus plus sine of plus minus n pi by 6 and sine of plus minus pi by 6. Okay? This is the expansion. So that will become for us cos of plus minus pi by 6 is root 3 by 2, and cos is an even function. So we can write the first thing as root 3 by 2 cos of n pi by 6. And you have a minus plus here. So notice that here you will get either a plus half or you will get a minus half, right? And here also you will get a plus half, plus sine n pi by 6, or you will get a minus sine n pi by 6. So the plus will combine with the plus and the minus will combine with the minus. So this product is going to have a positive sign. So we can write it as overall negative, negative, right? Right. We can write it overall as a negative half sine n pi by 6. And we have a minus cos n pi by 6 here. This is what it simplifies as. Now, what happens here is you can write this as basically half cos, this is 3 by 2 cos n pi by 6 minus 1 cos n pi by 6. You get a half cos n pi by 6 minus root 3 by 2 sin n pi by 6. And that is basically, this is cos pi by 3 and sin pi by 3. So this can be written as cos of n pi by 6 plus pi by 3, or that is basically cos of n plus 2 pi by 6. This is what you get. So finally we are getting 1 is equal to cos of 1 is equal to cos of n plus 2 pi by 6. So in general, that will be true when n is, this n plus 2 should become like a even multiple of 2, right? You can get a 2k. Actually, no, I'll just solve it properly. So you get 1 is equal to cos of n plus 2 pi by 6. The general solution of this would be n plus 2 pi by 6 is equal to 2m pi plus minus 1 is cos 0. So plus minus 0. So you get n plus 2 pi is equal to 12m pi. You can cancel this thing and you get n plus 2 is equal to 12m. So n is equal to 12m minus 2, right? So n is congruent to negative 2 mod m mod 12, right? Or n is congruent to 10 mod 12. Like n is a number like 10 or 22 or 36. Basically, it's negative 2 mod 12. Right? That's what we are getting from the first equation. From the second equation, if you look at the second equation now, you will get root 3 sine plus minus n plus 1 pi by 6 minus sine plus minus n pi by 6 equals 0. You can divide the problem into two separate cases and solve each case, taking the plus sign first and then taking the minus sign. What you will end up getting is this. 0 is equal to root 3 by 2 sine n pi by 6 plus half cos n pi by 6. This is when you expand this term minus sine n pi by 6. I am taking the positive sign right now, right? And this becomes half sine n pi by 6 plus root 3 by 2 cos n pi by 6. Same steps as before, and you get a sine n plus 2 pi by 6, right? And now this is supposed to be 0. So n plus 2 pi by 6 must be equal to a k pi. So pi gets cancelled and n plus 2 is equal to 6k. And n should be minus 2 mod 6, or n is 4 mod 6, right? So from the second case, you're getting n is 4 mod 6. And from the first case, you're getting n is 10 mod 12, right? So notice that the smallest number, both the results must be true, right? These two results were coming when we said the real part of z and the imaginary part of z are both equal to 0. So both the results must be true. So n can be 10 mod 12 and n must be 4 mod 6. So obviously 4 mod 6, what are the numbers that we get? We get 4, we get 10, we get uh, 16, and so on. And for 10 mod 12, we start with 10. So the smallest number which satisfies both is 10. So n is equal to 10 would be the smallest integer for which both the conditions are true. And basically, we have a root on the unit circle. So a lot of trigonometric identities were used here in this problem, and De Moivre's theorem was used, right? So That's how you sometimes see applications of trigonometry in polynomial questions. Let's look at another example. This is the next one. This says let A and B be real non-zero numbers, and let Z naught belong to complex numbers and it is not real, excluding the set of reals. Be a root of the equation Z power n plus 1 plus AZ plus NB is equal to 0, where n is a positive integer. Positive integer. We have to prove that mod of Z naught is greater than equal to the n plus 1th root of B. Okay, so Z naught is a root of this equation and it's a complex root of this equation. A and B are A and B are real non-zero numbers. N is a positive integer. So let's say Z naught can be written as mod Z naught cos alpha plus I sin alpha. This is the complex number representation, Euler form representation of this. And we know that sin alpha is not equal to 0 because Z naught is not real. That was guaranteed. Z naught is a complex number, it's not real. Right? So from the given fact that Z naught is a root of this equation, we can write Z naught power n plus 1 plus A Z naught plus NB is equal to 0. And what we can take is we can expand this and write it as mod Z naught to the power n plus 1 cos of n plus 1 alpha plus I sin of n plus 1 alpha. This is by raising Z naught to the power n plus 1 plus A mod Z naught cos alpha plus I sin alpha plus NB is equal to 0, right? So now this whole thing can be split into real and imaginary parts. Basically, this is like a big complex number. There are real parts like this, and this. And there are complex parts like this and the second term here, right? So since the whole complex number is equal to 0, just like in the previous problem, we will write two equations which will say the real part and the complex parts are 0. We get mod Z naught power n plus 1 cos of n plus 1 alpha plus mod Z naught times A times cos of alpha plus NB is 0. This is the real part. And the second part is the complex part, which is Z naught power n plus 1 sine of n plus 1 alpha plus A mod Z naught sine alpha is equal to 0, right? Now, what we can do is notice that there are lots of similarities between the two equations. So I'll try to simplify the two equations in this clever way. We'll multiply the first equation by sine alpha, multiply the second equation by cos alpha, and we'll subtract them. Okay. So we will get mod Z naught power n plus 1 sine alpha cos of n plus 1 alpha minus cos alpha sine of n plus 1 alpha. When we subtract vertically the first equation and the second equation after this multiplication, then here you notice that this term will get cancelled because top I have multiplied with sine alpha, here I have multiplied with cos alpha and I am subtracting. And finally you get plus NB sine alpha is equal to 0, right? So this term here is basically sine of alpha minus n plus 1 alpha. So basically that is sine of minus n alpha which is minus sine alpha, n alpha, right? So we get the equation mod of z naught power n plus 1 minus sine n alpha plus nb sine alpha is equal to 0. This is the equation we get. Now let's do that on the next screen. We have mod of z naught power n plus 1 sine n alpha is equal to nb sine alpha, right? And we know that sine alpha is not equal to 0 because z naught was real, not real. So we can divide by sine alpha and we can write the condition. Also, since sine alpha is not equal to 0, sine n alpha is also not equal to 0, right? N is a positive integer and alpha is not a multiple of pi. So what we can say is mod of z naught power n plus 1 is equal to nb sine alpha by sine n alpha, right? Now, there is a side thing that you need to prove here, a lemma, which is very easy to show by induction. What you can show is that mod of sine n alpha is less than equal to n times mod of sine alpha. This is a simple proof by induction. Take the case n is equal to 1 first. It is obviously true. Then assume that it is true for n is equal to k. And from there, try to prove that it is true for k plus 1 also. Right? So I will leave this proof to you. It is fairly straightforward to show this. So you should be able to do it. And now what you can say, because of this inequality, we can say that mod of z naught power n plus 1 is, if I take mod on both sides here again, I can write this as n mod of b mod of sine alpha by mod of sine n alpha. And we know that mod of sine n alpha is smaller than n times mod of sine alpha, right? So this is, the numerator has these two terms and the denominator is smaller than that. So this is clearly greater than equal to mod b, right? So we are able to easily show using this lemma that mod of z naught power n plus 1 is greater than equal to mod b, which implies that mod of z naught is greater than equal to n plus 1th root of mod b, right? So in the problem, we had to show that mod of z naught is greater than b power n plus 1. So we have already shown that it is greater than mod b to the power 1 by n plus 1, which is equal to b power 1 by n plus 1. Because b was a positive integer. Right? A and b were real non-zero numbers. N was a positive integer. So this is a real number. So mod b is going to be positive. Right? So this is, these two terms are equal. And we have shown that mod z naught is greater than or equal to b power 1 by n plus 1, which concludes our proof. Right? So in this problem, what we used was again the Euler form or De Moivre's theorem on a complex number, writing it in trigonometric form, raising it to powers, and then simplifying the complex number that results by saying that the real part of it must be 0 and also the imaginary part must be 0. Once you write those two separate equations, what we did was we just subtracted those equations after multiplying it with appropriate sine alpha, cos alpha, so that we could cancel the middle term. That helped us to reach the solution. Okay. Now, the next topic that I want to look at here is applications of the triangle inequality to polynomials. So first of all, what is the triangle inequality? It basically says that if A and B are any real numbers, any reals, we have mod of A plus B is less than equal to mod A plus mod B. And the same applies also to Z1, Z2, where Z1, Z2 are any complex numbers. Any complex numbers. we can show that mod of Z1 plus Z2 is going to be less than equal to mod of Z1 plus mod of Z. Now, you might be familiar with the geometric proof of the triangle inequality. What I will show you here is a pure algebra proof of this. Okay. So we want to show this, that mod of Z1 plus Z2 is less than equal to mod of Z1 plus mod of Z. So let's take two cases. Case 1 is Z2 is equal to 0. If Z2 is equal to 0, the inequality reduces to Z1 plus 0 is less than equal to mod of Z1 plus mod of 0, which means basically mod of Z1 is less than equal to mod of Z1, which is obviously true because they are actually equal. So now we will take the case where Z2 is not equal to 0. Z2 is not equal to 0. And in that case, since Z2 is not equal to 0, we can divide both sides by mod of Z2. So I will divide this side by mod of Z2 and I will get mod of Z1 plus mod of Z2 by mod of Z2, which is equal to mod of Z1 by Z2 plus 1, right? This is what I'm getting. And let's call Z1 by Z2 as a new complex number Z3, right? So we have left hand side of the inequality is becoming mod of Z3 plus 1. What about the right hand side? When we divide both sides by mod Z2, the right hand side is becoming mod of Z1 by Z2 plus 1, or that is mod of Z3 plus 1, right? So what we have to show now is that we have to prove this inequality. Mod of Z3 plus 1 is less than equal to mod of Z3 plus 1. If we can prove that, then I have proved my original inequality, right? So let's see how we go about doing this. So I have to show this. And here remember Z3 was Z1 by Z, right? So what I will do is I will take the square of this Z3 plus 1 whole square is equal to Z3 plus 1 times Z3 conjugate plus 1. So that becomes mod of Z3 square plus Z3 plus Z3 conjugate plus 1. That is equal to Z3 mod square plus twice of real part of Z3 plus 1. Why is this coming? Because Z3 plus Z3 conjugate is equal to twice of the real part of Z3. Okay? Now, we know that for any complex number, real part of Z is always less than equal to mod of Z. Right? This is a fact for any complex number. Actually, you also have imaginary part is Z. Z is less than equal to mod of Z. Right? So right now, so far we have mod of Z3 plus 1 whole square is equal to this. But now we can write it is less than equal to mod of Z3 whole square plus twice of mod of Z3 plus 1. And that is clearly less. Basically, now we are getting this part is equal to mod of Z3 plus 1 whole square. So what we have gotten is mod of Z3 plus 1 mod whole mod square is less than equal to mod of Z3 plus 1 whole square, which obviously means that mod of Z3 plus 1 is less than equal to mod of Z3 plus 1. And that completes our proof. So the main step here is using this inequality, right? And obviously taking two cases where Z2 is 0 or Z2 is non-zero. When Z2 is non-zero, we divide it by Z2 to construct a new complex number Z3, which was Z1 by Z, right? Now the triangle inequality can be generalized. So the general inequality is let Z1, Z2 till Zn be complex numbers. Be complex numbers. We have mod of Z1 plus Z2 plus mod of Zn is less than equal to mod of Z1 plus mod of Z2 plus mod of Zn, right? This is the general inequality for n variables. Also, I forgot to mention one thing. When does equality happen when you have a situation of the triangle inequality? So in the proof, remember we did this. Z3 plus 1 whole square is less than equal to, we got mod of Z3 plus 1 whole square. That's how we proved it, right? So here, the key step was we replaced mod of Z3 square plus 2 real Z3 plus 1. We said that this is less than equal to mod of Z3 square plus 2 mod of Z3 plus 1, right? So this was the key step where we said that this is less than equal to this. If you want to have equality, for equality, you can say that real part of Z3 is equal to mod of Z3, right? Real part of Z3 is equal to mod of Z3, which means that Z3 is a positive real number. Z3 is a positive real number, which means that Z3 was Z1 by Z2. So Z1 by Z2 is a positive real number. So the two variable triangle inequality is going to be in the equality case. Basically, if you have this triangle inequality, this is less than equal to mod Z1 plus mod Z2. Now, the equality case, which is this is equal to mod of Z1 plus mod of Z2, happens when Z3, which was Z1 by Z2, is a positive real number. That's what we have seen so far. And geometrically, this means that the complex numbers Z1 and Z2 lie on the same ray or the same line from the origin. From the origin. Only then will you have Z1 by Z2 is a positive real number. If they lie on the same line from the origin. You can try and think about why that has to happen. So this is the condition for equality for two variable triangle inequality. Similarly, for the n variable triangle inequality, which looks like this, in this n variable case also, equality happens. Equality happens when Z1, Z2 till Zn all lie on the same ray from the origin. All lie on the same ray from the origin, and in algebraic terms it means that Zi by Zj is a positive real number, is a positive real for all ij such that 1 is less than ij less than equal to n and Zj is not equal to 0. So Zi by Zj should also be positive real, just like in the two variable case, right? So that is your triangle inequality. The reason we have discussed it so much here is because it has numerous applications in complex number problems and also in polynomials. So one example that we can see right now is this question. So let a is greater than equal to 2 and x1, x2, xn be real numbers. Prove that the numbers capital A is equal to cos of x1 plus cos of x2 by A plus so on till cos of xn by A power n minus 1, and capital B is equal to sine of x1 plus sine of x2 by B, no, not by B, by A only, plus sine of xn by a power n minus 1. Prove that the numbers capital A and capital B cannot simultaneously be 0. Simultaneously or both be 0. You have to show that both cannot be 0 at once, right? So let's take the case where n is equal to 1. If n is equal to 1, you can easily see that A is simply cos x1 and B is simply sin x1. You are getting the situation a square plus b square is equal to 1, right? For n is equal to 1. So if a square plus b square is equal to 1, it immediately comes that both a and b cannot be 0, right? So the proof is very simple for the situation where n is 1. And now we are going to look at the case where n is more than 1, right? So we will say let n is greater than equal to 2. And let's try to prove by contradiction. So let's assume that A is equal to B is equal to 0. Both A and B are 0, right? So both A and B are 0 and we'll introduce some complex numbers. Let's say Zk is cos xk plus I sin xk, where k can go from 1 to n. So basically there are n complex numbers z1, z2 till zn, right? Then what is A plus IB? A plus IB is equal to 0 because both A and B are 0. But A can now be written as cos of x1 plus cos of x2 by A plus so on cos of xn by A power n minus 1. And you have plus I times B, which is sine x1 plus sine x2 by A, so on till sine of xn by A power n minus 1. And the whole thing is equal to 0, right? Now grouping this together, taking cos x1 along with I sin x1, I can write this as z1 plus this one becomes this and this get grouped together, it becomes z2 by A plus z3 by A square till zn by A power n minus 1 is equal to 0, right? This is the result we are getting because we have introduced some z1 to zn new complex numbers built like that, right? Okay, so we have this result, and what we can say is that z1 was what? Z1 was cos of x1 plus I sin of x1, and it is obvious that mod of z1 is equal to 1, right? Mod of z1 is 1. So I can write 1 is equal to mod of z1, and I already know z1 plus z2 by A plus z3 by A square plus zn by A power n minus 1 is 0. So what is z1? Z1 is negative z2 by A, negative z3 by A square, and so on, negative zn by A power n minus 1. So when I say mod of z1 here, I can replace that and take this negative sign outside and write it as like this. Mod of z2 by A plus mod of z3 by A square plus so on till zn by A power n minus 1, right? Great. Now in the question, we were given that A is greater than equal to 2. That was given in the question. So using the triangle inequality at this stage, I can write 1 is less than equal to mod of z2 by A plus mod of z3 by A square plus mod of zn by A power n minus 1, right? This is correct. This is coming. And notice that mod of z1, mod of z2, mod of z1 was anyway 1. Mod of z2 was also 1 because it was cos x2 plus I sin x2, right? So all the z's, mod of zk is also 1, right? So I can replace this as 1 by A plus 1 by A square plus 1 by a power n minus 1, right? By GP formula, this becomes 1 by a times 1 minus 1 by a power n minus 1 whole divided by 1 minus 1 by a. So I will do it on the next screen. We have 1 is less than equal to 1 by a plus 1 by a square plus 1 by a power n minus 1, which is equal to 1 by a times 1 minus 1 by a power n minus 1 by 1 minus 1 by a, which is basically this expression. If you think about it, this expression will be less than 1 by a times 1 by 1 minus 1 by a, right? Why? Because I have replaced the numerator, which is 1 minus 1 by a power n minus 1 with something larger, which is simply 1, right? And now when I do this calculation, this is equal to a minus 1 and a goes on top. So 1 by a minus 1. And a is greater than equal to 2. So 1 by a minus 1 is clearly less than equal to 1. Right? So what we have is a contradiction because we have 1 is less than this and this number was itself less than equal to 1. Right? So basically we are saying 1 by a minus 1 is greater than 1 and 1 by a minus 1 is less than equal to 1. Both the things are happening simultaneously. Right? This is the contradiction that we got 1 is less than this and 1 by a minus 1. Since a is greater than 2, it is less than equal to 1. So this contradiction means that both of a and b cannot be 0. We had assumed that a is equal to b is equal to 0 in this case. Right? So that is a contradiction and we have disproved that right now. Correct? Now, that's about it for today's class. We have seen some trigonometric applications for complex numbers today, and we have also introduced and proved the triangle inequality, understood when the triangle inequality becomes equal, and also seen an application where we applied it. In the next video on this section, what we'll be doing is using the triangle inequality in several problems and understanding how we can use it to get a sense of where the roots of a polynomial are. Basically, we'll use triangle inequality to bound the roots of the polynomial. There are many questions that come based on this concept. So the next video will be super crucial for you because you will learn about these standard techniques that are used many times. So stay tuned for that. That concludes our video today and hopefully you've learned something from today's class. If you like the content, please share the video with your friends, subscribe to the channel and I'll see you next time.